Okay. Hello, everyone. So good morning. We're going to start our post-keynote session with Adriana Stan. He's going to present off-the-shelf Hugging Face models for audio deep fake detection. He's going to talk about pre-trained Hugging Face models and specifically Wave2Vec. So, and how you can use this to detect audio deepfakes. So without further ado, I'm going to give you Adriana.
Hello. Hi. Hello,
Adriana.
everyone. For introducing me. I'll just go ahead and share my presentation and the code, and hopefully I'll get to make you all some very good audio deepfake detectors by the end of this very short session.
Great. We're looking forward to it. Thank you, Adriana.
Mm. Okay. I hope you can all see the slides then. Great. Good. So I'm going to be talking a bit about how we can start off detecting this very nice and latest trend in audio deepfake generators. So and see if we can counteract them using off-the-shelf Hugging Face models. So no training involved. So what are audio deepfakes? We've all heard about generating speech. So we mostly have two main ideas about this. It's either text-to-speech or voice cloning. And there's already quite a lot of major players out there, including some of the also the major companies like Google, Amazon, and so on. But all of these can now generate audio or speech, which is very, very close to human speech. And it can usually be mistaken or easily be mistaken as coming from a real human. So it's very nice in itself because it can help, I don't know, for example, visually impaired persons, or it can help generate online content in various languages and so on. But then it also has its very nasty part in the sense, especially in the cybersecurity area, where you can be fooled into, I don't know, sending somebody money thinking that they're your friend. Um, so what we're going to talk about is how to build a so-called deepfake detector. So we will have a training set, which consists of audio coming from real recordings, so somebody actually recording that speech, or fake audio or fake speech coming from these TTS or voice cloning systems. We're then going to use a so-called frozen SSL model, so a large self-supervised learning model that we already take from a pre-existing repository. We build a classifier on top, and then what we want to find out is, well, the fakeness score. Is this sample, I don't know, 100% fake or 1% fake or whatever? Or is it actually real? And then, of course, just having that classifier trained on top of this data does not mean that it will generalize well to unseen generators, as they come up every other week or so. So we have different TTS systems that can be built from week to week. So we're also going to try to see how this classifier that we build on some existing data performs on out of distribution data set. And we'll see some metrics which are usually well, which are common in the scientific community, meaning the equal error rate and the expected calibration error for this out of distribution data set. So I would have a question here, so it's less interactive, but I'm not sure how many people know about this SSL models. So these are self-supervised models trained on very, very large amounts of data. They don't require any labels attached to the samples for irrespective of the modality, for example, audio or video or text. And the way they go about this is to find this very interesting way of training the data, usually by masking it. So one very, or at least two very prominent SSL models in the audio modality are the Wave2Vec with its improved version Wave2Vec 2 and the WavLM models. So I'm not going to go into the details of the architecture. You can find more about this on their official papers or on HuggingFace page where they describe these two models in detail. So we have the Wave2Vec 2 and the WavLM. So Wave2Vec 2 comes from Facebook, and then WavLM comes from Microsoft. I'm sure, or at least I hope you've all heard about HuggingFace. So it's a very nice website or collection or hub, as they call it, of open source machine learning. So they provide extensive tools and models, or trained models on different tasks. And they also have this Python library called Transformers, which implements all of the latest Transformers architecture that are used in commercial applications. And of course, it's about community and collaboration. So you can talk to the people who deployed their models. You can actually create some apps and have your models tested easily off the shelf without having people needing to install lots of tools or I don't know requirements and so on. In terms of audio, the latest search I did included around over 1,000 models readily available. You can just download them through a simple line of code, and then you can use them in machine learning applications. So, for example, the Facebook collection of models includes the Wave2Vec 2, its extension to multilingual, XLSR, and so on. So you can just browse through these and try to find out what they do and if they're fit for I don't know, your application, AI application. And I'm not going to talk anymore about the details of this. I'm just going to skip to running a Colab notebook and see how we actually train this deepfake detector. Good. So we have this setup, importing the libraries and everything we need for it. We're also gonna use a data set. It's called ASV Spoof 2019. And it comes from a very nice challenge that's held, I think it's every other year now, in which lots of research groups or companies all over the world try to detect spoofed speech. So this is a different term for fake or generated audio, and it comes from the idea that initially what I wanted to do is to trick automatic speaker verification systems using text-to-speech generated samples into believing that those speakers are the real ones. So I'm not going to go through downloading this data now. You can do it, and I'll leave some links to the notebooks and the presentation for you if you want to. And of course, if you already have the data in your drive, you can just mount it and have it readily available. So what we also have, and I think it's going to be a bit tricky to switch in between tabs, haven't thought about this. We have this metadata associated to this data set of audios, which includes fake and real audios. And we're just going to read the information from there in one line. And hopefully I can share this easily. Yeah. So this metadata includes something like this, a list of files. These are the file names. And then these are the systems that the file names come from, the different TTS systems or voice cloning systems. And then we have an associated label, which is either spoof or bona fide. Bona fide is used for real speech. Okay, so we can load the training and evaluation data sets from the ASV spoof. We can also listen to some samples. I don't know if you can hear this. Hopefully you can.
We are not going to give away the store.
Yeah, so That's a spoof sample. It sounds a bit, well, not as good as you would expect it nowadays, but you have to think about this data set as coming from 2019, when the TTS systems were not as close to human speech as they are today. So now the sample, perhaps.
It was just another race in yesterday's history.
Okay, so this is even worse. So this is even worse than the previous one. And it may seem very easy to detect the spoof speech, but we can also listen to perhaps some samples where the recordings are really noisy, perhaps recorded in a very reverberant environment or with a very low quality microphone and so on. So although seemingly easy to do, the deepfake detection is not yet there. So there's different tricks that you can do and have the system fooled. We can then download and set up the Hugging Face models. This is just a class that we wrote. So we have this very simple so-called Hugging Face feature extractor, where we just get the models and this pre-processing step involved, where we take the audio and prepare it for the models, and then we just run the model over the input waveforms. So the audio is actually in waveform format, and then you just run it and get the embedding. So both Wave2Vec and WavLM, sorry, both of them take a raw waveform, so an audio, a recording, and project it into a so-called embedding. This embedding is, or you can obtain a embedding for every 20 millisecond audio frame. So you get this sort of like different type of spectrogram, if you're familiar with the term, where this type of spectrogram tries to abstract some more information rather than just presenting frequency, um, the frequency content of the input audio. So as feature extractors, so what we're gonna use are these two like base models, so the very easy and simple models in terms of these two architectures, SSL architectures, which are Wave2Vec 2 base, and this comes from Facebook, and WavLM base, this comes from Microsoft. So we can use them interchangeably. So once we set up this model, it automatically downloads the model, so you don't have to pre-download the model unless you want to. And it sets up everything so you can then just run it over your data. We can do the same thing for the WavLM base. Same thing. We'll now have two models ready to extract the embeddings that we want to use in our detector. So we'll also have to process all these audio files. We just downloaded the models. So now we're gonna load all these files that you've seen previously in the metadata. Yeah, and then read them through Librosa, and then pass them through one of the two models, either Wave2Vec or WavLM. And what we get here is a feature. Well, we call it feature. It's actually, as I said, a two-dimensional representation times versus embedding of the input audio. But for brevity and simplicity of this setup, we can then just average across time all these input features, and then we just get one vector. So it's just a simple array representing my entire audio. So then I can just put it into any type of simple classifier and get a predicted label for it. And we also construct an array of labels for those. And then we can save them, of course, as the NumPy file, but we're saving it as a dict. So it's easier, a dictionary. So it's easier to use later on. And this dictionary will contain the features, X, and then each associated label, and of course, the name of the file, just because we want to know which files it got wrong at some point. So this, again, I'm not going to run the notebook itself, but this is just a simple pre-processing in which only 36 files were processed here. We can do the same thing with WavLM, nothing different, just change the name of the model that you run over the audio data, yeah, and save the WavLM features somewhere on the disk or in Drive. So now what we got is from the entire, presumably, if we would run it over all the data, we would get two um, NumPy files in which we have the features, the labels, and the file names or file paths or whatever for both the Wave2Vec2 and the WavLM models. So these are stored, and now we can use them to train our classifier. So of course, I already have this data pre-processed, and we can just load it and read from it the keys for X and Y. We want to have the X as input and Y as predictions, the labels fake or real. And we now have 22,000 samples in the training set. Yeah, there's an official split for the ASV Spoof 2019, which includes a training set, a development, and an evaluation or a test set. So we have 22K training samples, and then we have around 64K test samples that we want to look over. What's also important to note here is the fact that, for example, the systems or the TTS or voice cloning generators used in the training set do not completely overlap with the test set. So we have new or unseen out of distribution systems in the test set that we're going to use as evaluation. We can just look at the data distribution, how many samples in the training set are fake or spoof, and how many of them are real, and the same for the test set. Of course, you can see that there's a huge data imbalance in between training fakes and, between the two classes, fakes and real. And this is consistent across almost any other deepfake detection data set that there is out there. So it's usually easier to gather lots of fake data from different generators than to collect relevant or lots of real audio data, although it may seem simple at first hand. What we would also like to do, just to inspect the data, and this is common when we try to work with audio especially, is to do some projections. So PCA would be one, but the latest trends in data projections or visualizations for, at least in the audio domain, is either the TSNE or the UMAP projection. So what we do here is take those embeddings that we generated before and project them using a TSNE algorithm into a 2D space. So we would like to look at the data that we have in a simple plot, for example, a matplotlib or whatever, and so on. And we do this and choose also different colors. What we see in red are fake samples, yeah, and what we see in green are real samples. So you can see that there's quite an overlap here. It's not a clear, of course, TSNE is not a linear projection. There's the samples in the high dimensional space may be completely separated or maybe not, but still it gives us an insight into how the data looks like. Because if you look across different data sets of deepfakes, then some of them may be very well clustered into fakes versus reals, just because, for example, the conditions in which the real recordings were performed are completely different than the conditions used in the training sets for the TTS or voice cloning systems. Yeah. We can also look at the test set. Similar, we have the red for fakes and the green for reals. Yeah, and again, there's quite an overlap there. What I also want to show is a projection of a TSNE projection of a different, it is the same data set, but we use a different model, a more powerful model, in which we can see that if we do some fine-tuning over these SSL models, then we get some better clustering of reals versus fakes. So here the black and green are real samples taken from either the training or the development set. And then here in red and magenta, we have the fake samples. So ideally, whatever we do or how we extract those embeddings, we would like to have this clear separation between the two classes, at least for the fake detector. Okay. So what we want to do next is to fit a classifier on top of these embeddings. Yeah, so we see that they're not necessarily very entangled, but still we may need a more powerful classifier, especially for the Wave2Vec2 base and the WavLM models, which are not as powerful as any of the newest versions for them. So for this brief tutorial, we're going to use the logistic regression on top of those embeddings, and we feed the training data and with it, sorry. That's going to run quite smoothly and fast, so we don't have to wait that much. And then what we get are the predictions for that logistic regression trained model, and we want to see how it performed. So we're going to print the classification report from Scikit. Yeah? We have the labels, the targets, and then we have the predictions here. And we also want to look at the confusion matrix, and we're going to normalize it to 1 so that we just see the percentage of correctly classified samples versus non-correctly classified samples rather than their numbers. So in terms of the classification report, we see that even with this very, very simple model, we have a 99% 0.99 F1 score, but this is over the training set. So this is just to check that the logistic regression was able to split our training set into fakes and reals. And of course, the confusion matrix is not perfect, but it's close to perfect, where we have a 95% accuracy for the bona fides here. So class 0 is for real samples, and class 1 is for fake samples. But then we move on to the test set. And here, although you would expect it to perform way worse, we still have a 0.97 F1 score, weighted average, given the fact that we have more fakes in the data. And the confusion matrix, again, looks pretty good from my point of view. We have quite a good accuracy for the fakes, not so good accuracy for the real samples. Another measure that we usually use in everything that has to do with binary classification for tasks where we can output a score is the equal error rate. So this is the point where the false acceptance rate equals the false rejection rate. So simply put, we just look off diagonal, off first diagonal, and see at which threshold, because this, whenever we do confusion matrix, we just set the threshold at 0.5, and then see what's above is class 1, what's below is class 0. But here we want to vary that threshold and see, for example, if I would to make a decision at 0.7, would that decision be better than, I don't know, all the rest? So we're just going to try to find a threshold where these off-diagonal bits are equal to some extent, with an epsilon, with a delta, very small delta. So then we just compute the equal error rate. And this is over the training set. Yeah, again, we just do an ROC curve, receiver operating curve. And from there, we intercept and find the equal error rate there. And we can see that we have the equal error rate, the smaller, the better, of course, because we want to have 0 values of first diagonal in the confusion matrix. So we have a training set of 1.24 equal error rate, and then this threshold, the threshold at which it set that decision, was 0.795. And we do the same thing for the test set, where of course we have a higher equal error rate, but the threshold is somewhere around there again. So we also want to see this, that the threshold for the two, well, if the two sets that we evaluate on are fairly similar. So it means that if I were to choose the threshold based and make the real life decisions based on the training set, that threshold would perform nicely even on unseen data. And then we can do the same thing for the WavLM. So I'm not going to go through this like line by line, but again, we can see these plots. They seem a bit more grouped. And what we can also see here is the fact that we have this sort of grouping in the samples, which may indicate that, which may indicate that these samples come from different TTS systems or voice cloning systems. Again, we can fit a classifier on top of that. We still choose the logistic regression, yeah, and get the same results, the classification report, confusion matrix, and the equal error rate. And we can now see that the F1 score for the WavLM is a bit better. Yeah, so we have an 0.99 F1 score for a training set, and then for the evaluation 0.96. And we can also look at confusion matrix here. I forgot, sorry, to make it into a normalized confusion matrix. And as final step, of course, if we already have the model, the trained model, we can then run it on any data that you have available or find some deepfakes online or some of your personal recordings and run the model over those to see what it predicts. Yeah, so we have this audio again.
He approached nearer to me. There were almost tears in his eyes when I had finished. Say it again, he seemed to be asking of me. Oh, say it all over again.
Okay, so this is an actual recording, but unfortunately, the model said that this is fake. And one reason that we can go again and go into the results and see where it did wrong. And this is very expressive. So usually the data that we have in our data sets is not as expressive. So this may have put off the models and the decision threshold in the logistic regressor. And of course, this is not it. This is only the start of a very basic audio deepfake detector. We're very much interested in looking at generalization, how it actually performs on whatever we see nowadays in the media in terms of deepfakes and how people are trying to fool other people into thinking that somebody said whatever. And we want to add new systems. So as I said, there's every other week there's a new system coming out in terms of TTS or voice cloning, and what we can do and how can we adjust our deepfake detectors for that. And that's perhaps one issue to be solved with continual learning. And then a newer, more interesting side quest of this audio deepfake detection is the so-called model attribution, finding out if this sample came from, I don't know, Microsoft's CTS or whatever, Amazon's or so on. So this is in terms of finding the source of those audios.
Adriana, we're about to end. Would you like to take a few questions?
Yes, sorry. Yeah.
Sure. So I think I'll just ask them since we're in time. Kamal and Sammy wanted to know how do you deal with data or class imbalance?
Sorry, can you say that again? Sorry.
How do you deal with imbalance in data or classes?
So data imbalance at this point is we're not actually dealing with it yet per se. We can of course subsample the fake data set or do some data pruning and so on. But as far as we saw yet in our research is this is not an issue. So the stronger models, if we were to go from wave2vec to base to wave2vec to XLSR, which is 2 billion parameters, then this data imbalance is not an issue.
And the next question is again from Sammy. It's about this embedding is big. He's just using PCA before logistic regression. Do you think that would be a good idea?
Um, so again, we looked a bit into these embeddings and how they're spread out and how the logistic regressor assigns. So the logistic regression should implicitly already learn a sort of PCA by weighting some of the coefficients more. So it would automatically learn their contribution to the final decision by itself.
Got it. Well, thank you for the excellent talk. We really enjoyed hearing you talk about audio and looking for deepfakes. So thank you again. And with that, I'll end the session. And thank you to the audience for being so great. Thank you.
Thanks, everyone. Bye.
Bye, Adriana.